Okay, fantastic. Now, I think I've seen Kaveh, who is on the session now. I'm just looking at this. Yeah, and this next session I'm going to do it with Kaveh, and I would also like to check whether the speakers now here, and is Gael here?
Yeah,
Gael,
I'm here. Tim is here.
And Tim is here. Who is going to present this paper? I suppose that Michel is not here at the moment.
No, he's not here, but I will present it.
Okay. And Gael, thank you very much, because I know that you have a time constraint. So what we're going to do is like the past three papers. So we're going to do the presentation and the questions all in one go, right?
Okay,
so
perfect. Yeah. Thanks a lot.
Could do, how long is your presentation? Do you have
maximum of 15 minutes.
Okay, so if you could do 15 minutes, and we could do another 15 minutes of Q&A, I think that would be quite good and quite enjoyable for you as well.
Do we have? I think that we have 3 papers in.
Yes, that's right. Okay. Because in the end, we also need to
30 minutes at the end for
questions as well.
Yeah.
And then Ahmed, is Ahmed here?
Hello. Yes.
Yes. Okay. How do you pronounce your surname?
Well, it's always an issue. Ahmed. It's like you have this sound.
Speak up. So I cannot hear you very well.
What? It's good like that.
Yeah. That's good. Yeah.
Okay. Like it's Ahmed. Like you have to have this sound, which is very specific.
Yeah,
the should come from
that's fine. I can pronounce it, but it's your surname that I have more of an issue. How do you pronounce that?
My surname.
Yeah.
Well, it's very hard also. Well, just it's called Ahmed Eldesoky. So, like, well, feel free to pronounce it.
As Eldesoky is fine. Yeah, I just wanted to. So that's fine. So I'm used to these names.
Very good.
And your co-author Nicola Colaninno, is she here?
Yes, they will join in a while. I think yes, at the time of presentations, they will be there, hopefully.
Fantastic. And who is going to present?
Yes, myself.
Okay, great. Yeah. And Juste. I saw.
Sorry. Yeah, I'm here.
I saw this name. Yeah, excellent. Yeah. Well done. Actually, you have a very good background as well.
Oh, thanks.
And Mike emailed me to say that he may or may not be able to join. Is that correct?
Yeah. He said he has an internet problem. So.
Yeah. So you're going to present anyway. So I think that'll be quite good. So what we're going to do is to do the 3 papers in succession, just like the 3 papers in the preceding session. So we'll do each one and discuss each one, and we leave some time to discuss once we've done it, and then to have a conversation as well. Right? And okay, without further ado, because I think this group, looking at the people, they're all kind of used to the AUM, the kind of approach, and also knows what the AUM is about. And these papers, they are not that different from the profile of the papers we had before in the AUM. And I'm really pleased for these high quality papers actually to have emerged in the kind of a lockdown or lockdown-ish conditions. So really pleased, and thank you so much. Now, and Gael, your surname is pronounced Lederrey?
Lederrey.
Lederrey.
It's really difficult if you're not a French speaker.
That's fine. I do. I pronounce it in the kind of American way, so that
exactly.
That in the United States. Lederrey.
Lederrey.
Gael Lederrey is a PhD student and also a doctoral researcher in the EPFL lab called Transport, right? So more or less I have pronounced this, which is a great place. Gael, perhaps you could say a few things about yourself, and then you can follow on to the presentation.
Yeah, okay. So I'm a fourth-year PhD student, and I'm closing in on the end of my PhD, and this is the second project I'm working on. I already worked on a project on using optimization techniques from machine learning and adapt them to use them on discrete choice models. And now I'm working on synthetic population generation, and we are trying to combine ideas coming from machine learning, so deep learning, these kind of things, but also experts' knowledge, because we are used to work with discrete choice models, and these models, we really value the expert knowledge to create them. So we're trying to combine the best of two worlds.
Fantastic.
And this is what my presentation will be about.
Yeah, and you also have been working with Tim Hillel and Michel.
Yeah, I work with Tim Hillel, who was in Cambridge. He did his PhD in Cambridge, and now he's a postdoc at our lab. And Michel Bierlaire is the professor in our lab.
Fantastic. Can you see what you can share your screen? If so,
yeah,
go
I
ahead
will share it.
And shoot.
Do you see the screen correctly, like the presentation? Okay.
Yes, that's right.
So,
wonderful.
Okay, so I will start my presentation. So my presentation is named Synthetic Population Generation Using GANS and Expert Knowledge. So it's a joint work between me, Tim Hillel, and Michel Bierlaire. I just want to tell you that this is still an early work. We are not finished implementing everything, so you won't see a lot of results, but the idea is to show you what our ideas and where we want to go. So the outline for this presentation is, first I will start with a bit of motivation, then I will talk about the state of the art, so the literature review, then talk a bit about GANS, and I will explain you what it is, some research perspective. I will present the DATGAN, which is our ID to do this synthetic population thing, and then I will conclude and talk about future work. So for the motivation, our motivation starts from the fact that agent-based simulation, they relies on accurate representations of the population. However, it's infeasible to obtain detailed socioeconomic data for the full population. I mean, there are issues with privacy, security, and also cost. So usually what researchers do is to use synthetic population. So yeah, so they simply don't use the full data. This synthetic population can be derived from collected data or completely created from scratch. So we looked at what has been done for population synthesis in the literature review, but especially for the transportation in the transportation community. So until 2010s, let's say, the main technique was the iterative proportional fitting. Beckman was one of the first papers showing this technique and applied it to transportation. And we've seen multiple improvements on this technique using hierarchical techniques, for example. There are still some people working nowadays on this, but less and less. Between 2010 and 2015, a lot of work has been done on Monte Carlo simulations. The paper of Farouk was one of the first ones to show that we could use Monte Carlo simulation to create such synthetic population. And then multiple improvements have been done in the future. Then between 2015 and let's say 2019, people have switched to Bayesian networks. There are one main paper about this. It's the Sun and Eraf paper. So this paper was really a bit groundbreaking and was really beating all of the previous techniques. And we've seen multiple papers using this and trying to improve it. But in the really recent years, especially starting in 2019, we've seen the use of deep learning techniques for synthetic population transportation. So the paper of Borisov is the first one to use a variational autoencoder. And we've seen the use of GANS in 2019 and 2020, and the paper of Badu-Marfo is one of the latest one and integrates multiple things into the GAN. So not just the population, but also like their OD matrix, these kind of things. So for the data generation in deep learning, so we need to understand why they started using GANs. So in 2014, Goodfellow created this generative adversarial network. There has been a lot of papers on these techniques, because since it started, like more and more people are starting to create new methods, but it's most of the time it's applied to images. There have been some propositions for tabular data, so the type of data that we could use for population synthesis, but it started only in 2018. And there has been only limited work on data representativity and convergence. It's missing a bit of a word, I'm sorry. So our idea was to start from the state-of-the-art techniques in deep learning, and then go to apply them and improve them for our needs in transportation. So let me explain you what is a generative adversarial network. So the idea simply is to train two neural networks. We train them simultaneously, and one is made so that it generates images, and one has to discriminate between fake and real data. So you can see the basic architecture. I mean, it seems a bit complicated, but if you want just something a lot more simple to understand what's happening, you have one generator that can have many different types of architecture, and his goal is to fool the discriminator. And this one is trying to, so he's trained with real and fake data, and then he's trying to make the guess if it's a fake or real data, and you train them once against them. So when you create the loss function for both, the loss is linked to the both of this neural network. So that's the idea of the GAN, training two neural networks against each other. And then, of course, in the case of population synthesis, we would get, once we have trained everything, we would get the data from the generator. Okay, so for the early models in GANs, the standard architecture for both neural networks, so generator and discriminator, were like artificial neural networks, really standard things. Then they started to make some improvements on the loss function because there were some issues with the training, also the training stability. So these two, the first two things are really about the training process of the GANs, because it's really difficult to train two neural networks against each other. And then I started to work a bit more on like, how can we create data that are, how to say, more representative of what of the real data set. And as you can see here, it's just an example of the evolution of generated data. This is with images. So you can see in 2014, we had some really blurry images. And in 2018, like, we could never imagine that this is a fake image. It really looks like a picture of someone in a really high quality. And so we decided, okay, we have these GANs. They seem to work well with images. Let's train them on simple 2D data. So just a blob of data. And the first things that we saw is that there are a lot of issues with them. Like, for example, the mode collapse is when the generator is like trying to get something that is really unrepresentative, but that will always fool the discriminator. So here, for example, you can see that it's not covering all of the real data that are the circles in a bit of a transparency way. We have a lot of instabilities in terms of training. For example, sometimes the generator is doing some weird things and then it's crashing and giving like some bad results. And when we get some good results, we have something that looks okay, but it's not like really representative of the data, especially in terms of outliers. We cannot cover them really well. So using early models is not the best thing when we have really complex tabular data. We can imagine like having census data has a lot of variables. It's not just 2D, and there's a lot of complexity between the variables. So early models are not the direction to go. So let me just talk a bit about the concept of representativity. So the idea that we want to do is not just create some new data and make them so that it looks like the one that we have. We want them really to represent and cover all of the original distributions, because when we are studying people in a population, we want to know about like the general people, but also like all of the outliers and why they behave like this, for example. So as I said, when we have original data, like we don't want something like on the left, we really want something on the right. So for this, we need to work on the loss function of these GANs, and we also need to have good assessment of our results, which is something that is quite difficult. So my two research perspectives right now, I have two of them and they are parallel. So the first one is the improvement of the population synthesis. So what we want to do is to develop some new robust machine learning models for this synthetic population generation. And the current state of research is the TGAN that has been done by Xu and Al in 2018. And the other one is the representativity assessment. So it's to develop some new statistical method to better assess the model performance. And the current state of research, at least in transportation, is the SRMSE, and has been developed by Müller and Axhausen in 2011. So this is quite old, and they haven't done a lot of improvement on this since it seems to work for them. But in our case, we saw that it's not always precise in terms of how to say, really finds some outliers of this kind of things. So I will talk about the TGAN because this is currently the state of the art in tabular data generation, but it has some flaws. So what you need to know, so the TGAN stands for table GAN. It has been developed in 2018, and the architecture for the discriminator is really like a usual architecture, nothing special, but they've done something quite clever with the generator. So they are using LSTM cells. LSTM stands for long short-term memory. So you have an example of what is an LSTM. Don't worry about everything that's happening inside. That's none of your concern. I won't go into details. I don't want to bother you with all of these equations. The only thing you need to know is that we are giving to these cells the output of the previous cell, the cell state of the previous cell, so like the memory of the previous cell, and some input. And then with that, we will generate an output for this cell, a new memory state, and we will pass this to the next cell. So in the end, we have sequences like this. The bottom arrows are the one giving the inputs. The ones going from left to right are the cell state and outputs going from one cell to another. And then we return the output as well to get the new data. So the two flaws that we found with this TGAN is that there's no specific relations between the variables in the dataset, and I will come to this in the next slide. And also there were some issues with the selection of discrete values, for example, because they used argmax on the predicted probabilities. So it means like it's the usual machine learning thing to do, but since we are working with a probabilistic model, we prefer to use like simulation to get these right discrete values. So what I'm meaning by this problem of like not having any relationship between the variables is this one. Let's, for example, have a data set with 5 different variables. We have the day of the week when the survey was done, for example, driving license, it's a binary variable, the age, the mode choice, let's say car or bike, whatever, and work status. In the TGAN, since this is how the data set was created and in this order of the columns, it will do it like this. So day of the week will influence driving license, then these 2 will influence the age, then these 3 will influence the mode choice, etc. What we want to add in this is a relationship between the variables, because for example, the day of the week shouldn't have any influence on the mode choice. It's just when the data was collected. So what we want to do is to add a directed acyclic graph to this. So a link between the variables. So this is clearly coming from us. We are not using any algorithms to decide whether we should put them in this order or not. We are just using our knowledge and what we have done with this data set to know what to do with this. So for example, here, I decided to put age that will influence on the work status, and this work status on driving license, and then the driving license will influence the mode choice. And the day of the week is completely separated because it doesn't influence any of the other variables. But then there are questions like, can we add multiple variables into one? Because the LSTM cell has been designed to be one sequence of cells. So you cannot have two cells going into one. So we are currently working, and this is the big implementation issues, to add multiple cells, because I don't see why age shouldn't directly influence the driving license and going through work status. They could be completely separated, and maybe we could have something else instead of work status and not have any relations between the two. So that's our idea of implementing in this that GAN. So currently it is somehow trainable. We did some hack, but we have not finished this implementing of multiple cells going into one, as I said. So there are multiple possible solutions, and I'm still checking which one are the best. So first we could concatenate the inputs and cell states, but then we had problem with size. We could use additional deep layers to reduce the size, but then the training will be a lot more complicated. Or we could simply transform the current LSTM cells to accept multiple inputs, but this requires quite some work on the theoretical aspect. So we are currently working on these different solutions. Yeah, and so we are really pushing to through this third alternative, and the first analytical results should be due ASAP. So as a conclusion, the GANs are the current state-of-the-art technique for population synthesis. It outperforms everything, either in transportation or in the machine learning community in general. So we propose this directed acyclic graph structure to add this expert knowledge into this TGAN. And as I said, in terms of future work, so we will finalize this implementation of the DAT-GAN, and also we will work on the validation and trying to define some different metrics to assessing the representativity of the newly synthetic population. And that's it for me.
Thank you.
Thank you so much. Yeah, and so at this moment, I would like to introduce Dr. Kaveh Jahanshahi. Kaveh, perhaps Gael, you could, or just leave this on probably. So Kaveh is here and you can see him.
Yeah, I can see him.
Yeah, that's right. And Kaveh is probably the most appropriate person here to talk to you. Great. Of course, Tim also has done a lot of work both with modeling and also with machine learning, but Kaveh has done similar, and Kaveh also comes from the Cambridge team, and he's now both working as a research fellow in the Martin Center, but also more importantly, he's now a senior civil servant in the UK Office of National Statistics. Kaveh, say a little about yourself, and then you can then just ask questions and ask away.
I was thinking that, thanks for the introduction, Ying, and I was thinking that actually I wanted to start the questions, etc. But now that you want to know a little bit about who I am,
you have to let people know that these questions are going to be quite sharp, right? So
sure. Yeah, my name is Kaveh, and as Ying said, that I've done, I'm working partly at Martin Center, but mainly most of the time at the moment at Office of National Statistics. There is a data science campus which is looking into applying and use of machine learning and the data science into various different things, from mobility to net zero to economy to EU exits and other things. Our team collectively looking into establishing pipeline, getting the model run, and providing the results into dashboarding and solutions for the decision makers. And the mobility is one of those squads that I am leading as well. And the book that you are talking about, synthetic data, is one of the things that we are deeply looking into, because, as you mentioned, we don't want to provide the census individual level data because of the security to research about. At the same time, you would like to have the data to be able to build your model base, and then the population synthesizers, and then the synthetic analysis is what we are interested in. So, I mean, the book that you just mentioned is really makes sense. I have questions, but I want first to open the floor to the participants to ask if there is any quick question that you would like to ask from Gael. And I assume that you can put it in the chat. Am I right?
Jamil's got a question.
Yeah, I do have a question. Thank you, Tim. And
here you go, Tim.
Thank you, Gael. This was a very interesting presentation. I just have one question with respect to the sequence of connections of your little boxes with the example of the day of the week. And how do you exactly establish you said that you do something based on your own knowledge of the situation. How do you exactly establish the connection between the different boxes and the sign of the connections, the intensity, the absence of them, etc.?
So we completely do this by hand, like thinking about which one should influence which. So for some of the variables, it's clearly easy to rule them out or these kind of things. But for some others, it's really up to interpretation, I would say, if you do it this way or the other way around, or if you connect two of them in this way or something like this. But it's just like we want to see how this could influence the results on the population that we create. Because I mean, for example, with the TGAN, we already tried to swap around the columns, so the sequence, and it doesn't have much influence on the results in the end. So we were a bit startled by this, because we didn't understand, like, if you put like some really important things like the mode choice, how, like, why would it be influence on the rest, and how the results are the same if you do it the other way around. So we started playing with this, and then we said, okay, there's something maybe to explore there. And it's also like the idea would be in the end, like, to have something that is a bit of a mix between the two. So you could specify some of the variables, but you don't have to specify all of them. And the one that you don't specify would be just put into like a sequence at some point. So that's the idea, like to not do everything and replace completely this sequence, but like if you're sure that this variable should influence this one, and this one shouldn't influence another one, then you can do this. For example, it would be interesting also for household and individual. When you create a data set that contains both, you could have like kind of two sequences, and then one that influences the other one at some point or something like this. But you could really separate some of the generation of the data.
I see. Yeah, it would be interesting also maybe to systematize it with some sort of principal component analysis or analysis to see like what drives what, and to exclude and like categorize it. That's very exciting in a way. Thanks.
Yeah, I mean, for the moment we are using PCA. Like the idea was to use PCA mostly for the representativity, but it's sure that it's also something really interesting to look at when we are creating this directed acyclic graph. I mean, there are many ways, like you can use some statistical methods to do it, or just like how you know from, I don't know, like previous discrete choice models that you build or something like this, I would say.
Thank you.
Right, thank you. There is also a question in the chat. It said that from Zhu Fang. Zhu, do you want to express your question?
I don't see the chat.
You can actually start talking, Zhu, if you're on the chat, or I can read the question. Okay, I will go ahead with it then.
Yeah.
So
sorry,
go ahead.
Yeah, can you hear me?
Yeah, we can.
Yeah, actually, in my understanding that the LSTM is to learn the short-long dependencies from different kind of cells or different parameters, say maybe which days or something like that. So this kind of dependency I learned from data, right? So this is a data-driven ideas. But if you use your domain knowledge to set up these links, in my understanding, it's more or less like that you forced to screen out or to shut some unreasonable or some links that learned from data. Is that?
Yeah, exactly. Yeah, that's the idea. I mean, I just saw your question and maybe I wasn't clear, but like when I wrote day of the week, it was like, for example, it just like referring a data set that I'm using right now. And in day of the week, they only have like the day when they did this survey. So, but it's not the day when they were doing their traveling, for example. But the idea is really like to be able to separate like different data stream that you would like to generate. For example, I think one of the first thing that we discussed with team was about this household thing, like how could we generate households and then individuals, or the other way around, because some people are working on this in the literature. And that's why like having different streams of data that can influence each other at some point could be interesting. But yeah, the idea is mostly like to remove some connections between variables instead of adding more.
But that kind of links can be actually, that kind of things should be learned from data rather than that you force to just like you hide your eyes and see that I never see that kind of links that's set up by data. I just right. Yeah,
I think that's, I mean,
OSTM, right? It's not a kind of a data-driven ideas, in my understanding. You just say that I hide my eyes. I never seen that kind of links set up by data. It's not to kind of interpret that. You are not trying to interpret that kind of links set up by data, right?
But it's true that we could definitely use. We could use a data-driven technique to then learn the best possible graph that would link these variables together. I mean, this is, yeah.
If I can just interject, that the LSTM is really about learning a time sequence. The idea is that we learn a dependency in a 1D going from left to right with a time sequence, and the idea to apply this to tabular data is completely false. We're not looking for seasonality in tabular data when we look for relations between columns.
The idea of LSTM is sequential data, but in my
and we don't have sequential data here, right? So the idea
you can learn the dependencies from the first parameters, right?
Yeah,
sequential
you
data.
can
may interfere here. So I think that we can leave this because this discussion is really interesting, and we can leave it for the last half an hour so that we can first of all open rooms for other questions and also get on with our next speaker. I mean, to summarize a little bit here, I think that one of the issues generally with this type of directional effect is what we call the structural ambiguity. Is exactly that what is affecting what. But there are ways around it. You can try different structure. You can have the ensemble of models. You can get the machine learning to find out what the best structure is, looking into the goodness of it, your data or your posterior distribution, etc. So I assume that, I mean, it's interesting discussion to have how we are separating, first of all, LSTM from that side of the work, because one is about the sequence and the other one is about finding out the structural relations between the data. But let's take it to our half an hour discussion at the end of the session, perhaps, and have it more than if you all agree.
Kaveh, there are a couple of texts in the chat as well.
Sure. So I would just take it. Shall I go through the next chat, or shall we?
Yeah. So perhaps go through that, and we could end there, because I think we have got.
So yeah, sure. So the other one is from Marcelo, who's asking about the day of the week, and said that, Marcelo, do you want to actually unmute yourself? And
okay, thank you.
But since you are here, right? So ask live.
Yes.
Yes, I'm here. Okay. The day of the week, to me, on an individual level, I think it has influence on module choice. Of course, this is a very personal thing and not doesn't work for everybody. I don't know how you put this in your simulation, but I used to base my module choice on the activities schedule I had for a day. And usually Thursdays, I had to be very early at work and public transport was too crowded. So I would use my car, which I don't like. And days I would prefer public transport because although it takes longer, it's less stressful. Mm-hmm. Also, some cities have implemented restrictions for traveling based on license plate. So if you own a car, 1 week you cannot use it on the peak periods because of your license plate number. So people would either buy another cheaper car, which is very bad, but happens, or they would go by public transport. And this in the long run has changed behavior, at least in my city, which is São Paulo, Brazil. Okay, so I'm just commenting because I think maybe there is a link between day of week and module choice, which would be something, as you said, statistical, it's a probability.
No, I totally agree with you. I think it was just a mistake by myself, just a bad wording, I would say, because I didn't mean day of the week as the day when you're traveling. I meant as the day when the survey was made. So I should have used something else, and I'm sorry about that. Of course, the day of the week would influence it, especially because even if it's like the weekend or the weekdays, like we don't use the same transportation means since we have to work or sometimes not. So yeah, day of the week would definitely influence on this. So yeah, it was like my mistake, sorry.
Also the type of the motive for the trip.
Yeah, of course. I mean, here I just took an example with 5 variables because I didn't want to have a big slide with a lot of things. But I mean, usually data sets have like tens, even hundreds of variables. So yeah.
Okay, thank you.
Yeah, that's true.
Welcome.
Thanks a lot. I assume with no further delays, let's start for our next presentation. Ying, do you want to do some introduction?
Yeah, that's right. And this is actually my test of pronouncing the name. So there are 2 names to pronounce. In fact, we're delighted to have this second presentation, which is coming from Italy. And Ahmed Eldesoky from this is Università Iuav, right?
Yes.
The Venezia. So it's basically it's a university that grew out of an architecture school. I'll be very proud of it because I trained as an architect myself. And his paper is a collaboration with Nicola Colaninno from Politecnico de Milano. So Ahmed, perhaps you could say a little about yourself and then proceed to the presentation.
Okay. Hello, everyone. Good morning or good evening. I don't know wherever you are. I'm Ahmed, as you were presenting and you were saying, and I have a background. I have a bachelor in architectural engineering and a master's in urban planning with a specialization in climate modeling. And I'm a PhD, currently a PhD candidate in urbanism at the University of Venice, as you were highlighting. And my interests are usually in urban climate modeling and urban morphology in general, and what's the relationship between both of them. So today I can jump directly to the presentation. Okay, don't know if you see it or not. You see my screen?
Yeah.
Okay.
Very well.
So as I was saying, this presentation, this work of today I'm doing it with my co-supervisors, as you were introducing, Professor Nicola Colaninno and Professor Eugenio Morello, which I think he's around. I have seen him. So basically, this work is a bit different in a way that it's more about data itself and making data available and creating data and making it accessible. So it comes as part of my research. So it's not the main goal of my research, but it's just something, since we are doing an evidence-based research, we need data. And in the context that we are working, we don't have such kind of data. So the goal of today's presentation, just to give you an idea of how we created this data and our plan, how to make it publicly available and accessible. So from title, as you see, it's high resolution air temperature mapping in a data scarce area, but also an arid place, which is in Egypt, within the context of Egypt. And the main idea is to use low-cost mobile measurements for air temperature with applied machine learning. So just to give you like an overview about it, of course, all of us know that in urban areas, extreme heat waves and the urban heat island effects are clear demonstrations of climate change. So it's obvious, and also they have critical and serious impact on critical infrastructure in general and on human comfort and health, if we say. So these small differences from seasonal average temperature also matters, and only half degree of global warming is a big deal. And with heat waves becoming more severe and frequent across many parts of the world, the interest in better understanding the urban climate phenomena and the micro one, particularly, especially the spatial variation in ambient air temperature, has been becoming of more interest, of particular interest, especially in academia or even in city planning practices. Air temperature as a variable is not only important for health of humans, but it's also important for other processes, biotic or abiotic ones. For instance, it influences plant species, their growth, and that's why it's always, as an indicator, it's usually used in many modeling and in many models like evapotranspiration and hydrological models. So since we are interested in measuring air temperature regarding planning and design, particularly, so we are more interested in this layer of atmosphere, which is the urban canopy layer, which is the layer below the roof level, which is the lowest one on the scheme on the right, because that's where most of the human activity actually happens. And the method to observe air temperature or the climate of this layer usually comes from weather stations or observations from weather stations. But the problem that we always have is that we don't have always these weather stations, these fixed weather station available. And even if they are available, they are not evenly distributed. So we can have them focused in specific places in the city or the territory. So they are not evenly distributed in a way. Furthermore, if we go to less developed countries, we can even have more difficulties finding any kind of weather stations. And also, if we are planning to fix a whole meteorological network of fixed weather stations, that can be in a way expensive somehow, but also it's not always possible to fix weather station, maybe because of complexity of the lantern or whatever. So, but with advances in sensor technology and the Internet of Things, we have observed over the last years big advances in sensor development, even with low prices. So we have such kind of open access air temperature data from fixed weather stations, which actually are private weather stations purchased by normal people in their houses. But this information, because of the Internet of Things from these devices, are made available. But also it will depend which part of the world we are. Some parts we have more stations, other parts we don't have. So it can complement the municipal or the regional weather station network, but we can only rely on that in specific places, as in my case. So other methods for observations in the urban canopy layer, which is the focus of this work, that when we use mobile measurements, have sensors, these sensors mounted on vehicles that can be cars, bicycles, or even carried by humans to pass across different microclimates or different parts of the city. These mobile measurements can be very useful to complement observations from fixed weather stations. At the same time, they can also help to explore some parts of the cities that are rarely explored, or where we have so much large spatial heterogeneity. But the problem here remains. Whatever data we have, either from weather stations or from mobile measurements, these data are discrete in nature, meaning that they are punctual data. So they are points that describe specific locations. But what we are more interested in, what we are liking to really have, is that we have a continuous surface, a kind of gridded data, so that we can observe whole cities or territories, or places that we really don't observe or cannot reach in some ways. So such a kind of data that available right away from air temperature data, usually they come at the very coarse spatial resolution. So we have a continuous surface of about 5 kilometers or even 2.5 kilometers, which doesn't really fit micro and local climate investigations, which usually happen at 100 meters. We speak about 400 meters or 500 meters, which is a neighborhood scale in a way. So having an information about 5 kilometers can be too coarse for such kind of investigations. That's why there has been investigations. How can we provide such kind of air temperature data at a higher spatial resolution? We speak about 30 meters, 50 meters, even 100 meters. So how can we provide such kind of data? But itself, predicting air temperature as a variable, as I was saying, and also as was introduced this morning, relies on many factors like urban morphology, land uses and land cover, anthropogenic heat, the wind speeds, the cloud cover. So there are many factors. But thanks to the modeling techniques, there are many ways to model such kind of air temperature at this high spatial resolution. And one can classify them into interpolation techniques, regression, or simulation ones. So just to give you an idea, like for interpolation techniques, usually the problem of interpolation techniques that they require to have a spatial uniformity of the observations, which is actually not the case of weather stations, neither in the case of mobile measurements. We usually have these measurements, but unevenly distributed, which makes interpolation techniques usually not very successful in predicting temperature data with high accuracy, let's say. But on the other hand, there has been like a big trials on using regression models, but specifically regression models that include spatial heterogeneity, which is like geographically weighted regression, which can be very ideal for such a kind of investigations and prediction, especially with climate data, which is non-stationary data. And below you can see two examples from my colleagues at Politecnico University of Milan, when we applied different modeling techniques from interpolation and from geographically weighted regression. And of course, seeing the interpolation techniques, they seem like they can give an idea, but it's still not possible for this kind of local and microclimate investigations. So another technique, which I think all the audience in this session particularly are familiar with, which is random forest regression, which is, that's why I just speak very generally about it, which is a machine learning, non-parametric machine learning algorithm using in simple learning for making predictions, especially for non-linear relationship. I would say that last 3 to 4 years, this regression model, this regression algorithm, machine learning algorithm have been widely used with mobile measurements to provide high predictive performance for air temperature. And usually it operates, as you know, by having some decision trees and bootstrap data sets with random subset of variables. And then we can observe each indicators based on the models that we just have trained. In fact, as I was saying, the approach is not completely new, and the methodology has been already applied and tested in different cities. What we are aiming for here is just adjusting the existing surveying and modeling approaches to fit an arid place, which is a specific place in terms of land cover and property, but also to test the effectiveness of the approach, particularly when we are using low-cost instrumentation, but still with high accuracy in sensing, and also using completely freely available predictors, which in this case, freely available satellite data that comes from Landsat particularly. As I was saying, the ultimate goal here is to provide accurate air temperature data for research and practice in a data-scarce area, but also an arid place, and making this data available and accessible for everyone, let's say. So as I introduced before, the case study that we have done such a kind of investigation is a new desert city within the greater Cairo region in Egypt. And as you see from the left, in Egypt in general, we have very few meteorological stations, meaning that having 127 over a whole territory of 1,000 kilometers by 1,000 kilometers is very few. And particularly if you see at the right, our context, which is this one highlighted in gray, we almost has no weather stations in the nearby. That's why we don't have, let's say, any information regarding weather station in this case. So the methodology, in a brief terms, the premise here is that there is a direct relationship between land use and land cover in general and air temperatures or near surface air temperature. And as in any regression model, we need a dependent variable and predictors. In this case, our dependent variable is air temperature that comes from mobile measurements, and our predictors are indicators from satellite imagery that are able to distinguish between the different properties of land use and land covers in arid places. So as a first step, we got such kind of mobile measurements. We corrected the data and processed it, as I will show you in a while. Then we use this data to feed the random forest model as dependent variable. And on the other hand, we got satellite imagery, freely available ones, made some image processing, retrieved some indicators, and then use them as predictors in the random forest model. And then we have evaluated the model, trained the model, evaluated the model, and used this model to predict the whole temperature for the whole city for different days. Just to give you an idea about the survey and the design that we have done. So the measurements were conducted using a relatively low-cost wireless weather sensor with GPS that is built in. And this GPS and the whole device is manufactured by an American company, which comes as a very relatively, let's say, low price, which is $400 in general, which is compared to a whole meteorological network of weather station is nothing. The good thing is that this sensor, even with low price, it can measure up to 18 different measurements, including air temperature, relative humidity, but here we are just focusing on air temperature, but also comes with a very high accuracy in terms of air temperature, which is 0.02, which is compared to other studies and sensors, it's relatively really very high. It also has a very high resolution, which is 0.01 degree. This sensor generally was mounted on a car that moved at a speed between 15 to 60 kilometers based on literature, so that we can maintain an adequate ventilation for the sensor, reduce any radiation errors, and so on. And in total, we have conducted 4 campaigns on 3 different days, both during daytime and nighttime last September, under suitable meteorological conditions of low nebulosity and low wind speed, which fits microclimate or local climate measurements. So usually the daytime observation were at solar noon, which is where we have most energy from the sun, but nighttime one was like 3 to 5 hours, which is the time where the urban heat island is most maximized. For each session of the 4 surveys, it ran in between 2 to 3 hours so that we can maintain, let's say, stable background macroclimate conditions. However, this is one of the limitations of mobile measurements in general, is that we have to do them over like time interval, then we have to correct for that. So the campaigns were conducted along a predefined route that crosses different land uses and covers and morphologically different built-up areas. So previously we have identified 7 different urban types or morphologies, which we know that they have impact on microclimates, and our survey should have crossed all these different typologies in a way. So the maximum, let's say that then once we got this data for the different surveys, we had to make some processing, like excluding measurements recorded when the car speed was very low or when it was stopped or when it was very high. Then we had to correct for the cooling and warming that I was speaking about. And we can see that from the graphs that going on with time. So we have a kind of cooling effect, and then we had to correct for that, but also to remove the effect of elevation changes. And overall, the maximum daytime observed in this case was almost 38 degrees, and the lowest was 33 degrees in general. But during nighttime, the maximum and the minimum temperature, we can see very clearly that they are so much lower, which is 32 almost or 28 in general. So then the next step was these processed temperature data from the different campaigns were geolocated using the GPS data from the sensor, where one can already observe some spatial variation in air temperature across the defined route for both the 4 surveys. We will speak about that in a while. As I was saying, our models requires dependent variables, which were air temperature collected from the surveys, but also predictors. And in this case, our predictors come from Landsat imagery, where we processed for a specific day to retrieve different indicators. These indicators are the soil adjusted vegetation index, and it's a very important indicator that reflects the density of vegetation, since we know that there is a relationship between air temperature and vegetation intensity. The second one was the normalized difference sand index, and it's a remotely sensed index that distinguish between sandy desert or bare soil in general and built-up areas. And the last one was the normalized difference built-up index, and from its names, it's an indicator where higher values represent more built-up areas. So these are the 3 indicators that were used as predictors. But one point here is that air temperature is influenced by land use and land cover within varying distances, which is like tabular first law of geography. So we have different buffers of zones that we can say air temperature in a specific location is influenced by the surrounding. That's why it was important to account for these spatial dependencies in our random forest models. And we did so by transforming each of these indicators by applying a moving window calculation to estimate the average value at each location within different buffer distances that ranged from 50 meters to 1,000 kilometers. Then the process temperature data, as I was saying, were used with 45 predictors, which are the 3 indices with different 15 buffer zones. So we have 45 predictors at the end, calling them multispectral, multivariable indicators to build the random forest models. These random forest models was evaluated for the best number of trees, the efficient number of trees to reduce the computation time, also for the number of variables at each split or each bootstrap. So since we don't have a separate data set, as Hillel was speaking this morning about validation, so I mean, we don't have a separate data set because we don't have this information as a city to make a kind of external validation. Our models are validating using a cross-validation with a repeated holdout cross-validation, let's say, by subsetting the original data set into training and testing for multiple times. And all the 4 models showed high predictive power with a coefficient of discrimination like 80–70%, which was the lowest thing, which I think is very high, but also with a very low variance in error, which is 0.018 degrees Celsius. Also, daytime models have showed lower performance than the nighttime, which also something was confirmed in previous studies, saying that during daytime we need more other predictors to predict air temperature, not just land use and land cover, but maybe building height information, which is information that might not be available in this case. That's why the main goal here is that, okay, we are just using freely available satellite data. Then this random forest model were used to predict an air temperature value for each location that was not visited by the vehicle, and hence producing a continuous or graded air temperature maps. So these are the final results, which are high resolution air temperature maps for the entire city for multiple days during daytime and nighttime. And as I highlighted at the beginning, these maps can be used for various applications, especially in understanding the impact of urban form and function on micro and local climate. As I was saying, our plan is to publish these maps and make them freely available and publicly available to everyone. However, just to give you an idea about possible applications in urban planning and design, for instance, from these maps, one can observe clear patterns of the urban heat island already, or the cool island in some cases, with variations of air temperatures up to 2 degrees during nighttime or 3 to 4 degrees during day. Also, these patterns are consistent for the different days or times observed. As you see, so more or less the same pattern that we have. But one interesting thing is that during daytime, the city has a cool island effect, meaning that the central residential areas, as you see these places in blue, they are cooler than the surrounding desert, which is also typical for arid cities in general. If we go more, let's say also that the impact of industrial or production activity, which is located in the southwest of the city, highlighted in this red square, is apparent on the air temperature during both daytime and nighttime. By having a closer look, one can also observe that during nighttime, lower density urban areas with absence of vegetation are cooler than high density areas with sparse or without vegetation at all. Also, commercial places or big shopping malls, which something is widely you can find in this new desert development in cities, in Egypt particularly, show relatively higher air temperature, not only in daytime, but also nighttime, but also they amplify the heat in the whole surrounding. As just highlighted in the large scale image, central urban development show lower air temperature during daytime or a cool island effect as a result of the shadows that usually casted by the tall buildings or the compact urban environment, which reduce the amount of solar radiation received by ground surfaces. And here I'm just coming to one more thing, that one can also use this temperature data to study with more precision the impact of different building typologies or urban forms on the micro and local climate. Like in my research, we are using this data to evaluate the performance of site-specific typologies in terms of resilience to heat stress. So we can draw some insights and recommend planning and design guidelines at a very local scale. For instance, building in an open arrangement with large open spaces, as you see from the left, however, with no means of green space maintenance or management, like in this example of public housing, can make this typology extremely vulnerable to high heat stress. Similarly, if you look at the more private residential schemes in these places, which are aimed for high income population and usually found in gated communities, they have more green spaces. That's why these places are less exposed to extreme heat, but it's not necessarily means that they are resilient if we speak about resilience from a broader perspective in a way. And yeah, last thing I would say that also the same in industrial places, we see these places with extensive previous surface cover with high traffic, and we should give more attention to the design of these places since it shows the highest temperature recorded ever during our surveys. Just to give final conclusion, just to wrap up, as I was saying, accurate, continuous, or graded air temperature data are very essential for many research, including climate responsive urban planning and design. mobile measurements in this sense, when combined with freely available satellite data, spatial analysis, and statistical modeling techniques, can really provide opportunities for better mapping and observing local and microclimate. What we were really aiming for in this study was providing and making accessible, accurate data, temperature data at high spatial resolution in a data-scarce area. The main contribution in this work also lies in adjusting an existing surveying and modeling approaches to fit an arid place and to test the effectiveness of these approaches, particularly when using low-cost instrumentation and only freely available satellite data, so that the approach can be replicable in similar context or conditions, let's say. And yes, and that's it.
Thank you so much. We might have not much time, maybe one or two very quick questions if the audience have any. That was really interesting presentation. Thank you. I'm interested to see how data is collected and then it can be fused with other data from the land use to transport and the mobility we just discussed for more insights. So any rapid question for now from Ahmed?
Coverage as a point that I think because if we're going to do the 3 papers separate because the topics are quite different, we could do each one with 40 minutes, and effectively the first paper by Gael was 40 minutes. So
I thought that you want to keep 30 minutes at the end, so that's not the case.
Yeah, so I think that how it evolved, I think it might actually be more.
I see. Okay, so we have more time. Great. We have 10 minutes or so.
Right, yeah.
Brilliant.
So
in which case, we have more time for questions. I encourage people to come forward. I have some, but just wanted to give the opportunity to others to first ask their question.
Well, I think it's say yours, and then perhaps then.
Actually, we have one in the chat already. So one is, have you investigated using other variables such as wind from the sensors? And that's from Sam Bland. And if you want Sam to elaborate more, you can unmute and talk. So Ahmed, I think that.
Yeah, no, I was waiting for Sam. No, I was waiting. Okay, no, that's a point that maybe some things that I didn't say during the presentation. That one of the limitations of mobile measurements that they don't fit really wind speed measurements because the device or the sensor is fixed over a car that's moving at a relatively mid speed or high speed. So such a kind of observation is not really compatible with, let's say, with wind measurements. And that's one of the limitations of mobile measurements in general.
And I also have a question. I mean, you somehow touch on this, but it's about the spatial correlation, specifically that when you're moving sensors around, you might get measurement biases differently from one area to the other. How did you deal with the measurement bias? Did you try to validate it through different sources, or have you looked into like a time series variation or something to look at into that? Or have you considered it for the future research?
No, but yeah, this was one of the things, and that's why we tried first to evaluate the model using different buffer distances. So let's say we started with 50 meters, then 100 meters, then like adding more and more and more. So one of the things that first we evaluated which let's say best buffer distance that can make high predictive model, and then we found that by combining different ones, we could actually correct for such a kind of bias. So there are 2 ways, let's say, that we check first which buffer distance fit which indicator, or we can use multi-distance and multi-indicator way, in a way.
And when you say multi-indicators, you mean multi-different measurement way or multi-different variables?
Multi-different variables.
All right, okay. Great. So looking into like the satellite images as well as the sensors, etc., and then combine them to get into that. Any other questions from the audience? Tim has one.
There's the raised hand feature as well. I don't know if, but thanks a lot. It was a really interesting talk, and I Kaveh was thinking down exactly the same line as me in terms of spatial and temporal correlations. And so I was just wondering, I heard you reference the earlier talk. I was just wondering if you could elaborate a little bit more on the cross-validation procedure you applied in terms of how you controlled for those biases with your sampling, because it's a really interesting case study to have to deal with both of those biases at once. So if you were able to elaborate more, I'd be very interested.
Well, that was one of the limitations, and I wanted to have, after your presentation this morning, like some more doubts came in actually, because yes, this is one of the main limitations, because we don't really have this kind of different data set. And as what Professor Batty is saying this morning, that okay, if you want to test a model, just bring it to a different case and then we can test it. But with temperature data is something very specific, very local. So this is one of the things that we start raising the question, how can we then, if we don't have an external database, how then we can validate this data? So using cross-validation, using repeated holdout, we subset the data to different data sets as training and testing. Is it suitable? Can we use that data set that measured in a different day to validate the data that we use to measure a specific day or no, considering that we have different meteorological, even if we have the same pattern, let's say, but it's still measuring two different days, two different timings. So how can we do that? Well, still not sure about it. And yes, this is one of the things that really like makes me a bit,
maybe in case that it add some insights. I think for the work that we're doing on COVID these days, and the COVID is everything, and then at the moment is maybe lots of interesting stuff can come up out of that, like reporting measurements and the measurement error in the COVID reports are both spatially and temporally biased in a way, because they are systematic. So for instance, when you have more cases of the COVID, like in the dense areas, I mean, at the start of the pandemic, those dense areas are underreporting the cases because like they were really busy compared to area that were like not that as busy. And also over the course of the time, the test and trace and other apps, etc., within the UK has improved. So the reporting started improving in terms of reporting the real things. So the way that sometimes things works in terms of like controlling for those measurement errors is both from the variable angle that you just mentioned. So different variables can have a similar communality. For instance, on the COVID, one of the projects I'm trying to get my head around, I mean, and we are leading, is looking into the boots data to give us sort of like a drug sale, and then compare it with the last year trajectory to see increase in that, and then completely like as an instrument, and then look into the COVID cases, and then do a sort of like a factor analysis to see where these things are most communal with each other, have similar pattern or have similar measure to share, where they are different. As you mentioned about like the different sort of indicators come together. A factor analysis is the most simplistic way, but there are other ways of like trying to find out and cancel out a measurement error. The other thing is true, actually, if you have one variable, but you have it over the course of the time, things such as the model that just Tim and Gael as actually referred to last time, some model like local transition models, which is looking into you have a true measures, and then you have the actual measure, and that true things is a latent variable which works as a sort of like a transition behind the actual measures that you can measure over the course of the time. And you're actually seeing the actual measure, but it's based on it sort of like a transition. And then you have a theta or a bias, which is also added to that format. And then you can look into things such as, I don't know, the gamma distribution of like how these things are how the actual value is changed, and what you can say about the actual value as you're predicting the next time episode, from the starting time episode to the next time episode, etc., while they're also predicting the actual measure that you get. So the true value and actual measure, true value is a latent variable as a mechanism behind the actual measure. There are, again, models like these sort of like latent transition models, which can look into like modeling that, and in terms of the cases, actually measure, and even the rate of changes in the basically, even it can be two levels. One level is actually the true value. Second level is actually rate of changes in the true value, and then both can work together to make it even more accurate. And you can then fuse or integrate your other variables into these latent values to get a bit more information. But we can discuss this question also. This I don't want to take all the time. Any other question? I mean, we have one from Ali Soltani. Ali, do you want to actually express your question? Unmute and talk.
Or I can answer.
Or you can answer. Yes, it says that. Thank you for your great presentation. Do you think the spatial scale of a study does affect the accuracy of results?
Yeah, but I mean, what do you mean by spatial scale? Is it like a spatial resolution of the data that you're using, or the buffer distances, or the buffer scale? Really?
And if you're present, you can ask your question, or I mean, elaborate, or you can type either way.
Thank you for being here and giving me an opportunity to ask a question. My question is that because such kind of studies are done in different scales, street scale, neighborhood scale, campus scale, and city scale, my question is that because the variation of the data is changed when you change the scale of the spatial scale, so do you think if we repeat this study for a larger area, say for urban district or urban neighborhood, what would be happen for the accuracy of the result, and what will be the difference between a larger scale study and such kind of a smaller scale study, which we assume that the variation in temperature is low? So thanks.
Yeah, I would say that from my experience in this, as we go far with like a coarser resolution, we can have really improve the accuracy of the model. So, and actually this most of the data that are existing, which are like 500 meters to 1,000 kilometers, they are really high predictive performance, so, because you aggregate many information at the level of the pixels. But the goal here is that we start from the very low scale and then we go up with the scale. So all our observations comes at the very low scale, so which is the street scale, since we have these measurements in the canopy, or let's say in the urban canyon at the street level. Then our satellite data also fits this scale, since they come at a very high spatial resolution, that's 30 meter by 30 meter. So our data comes from this lower scale, and as long as we have higher predictive performance at the very lower scale, absolutely, I would say going up with the higher spatial resolution, the spatial accuracy will be even more higher. But it all depends on which kind of analysis you're studying, what kind of scale. Here we are interested in micro and local climate, so we are restricted to 100 meters to 400 meters, let's say. So this is the whole point. So we start from the very low scale in a way.
Right. I can see that there are some raised hands, but I can't see them. So let me have a look. No, apparently we don't have any other raised hand that I can see. So with no further delay, sorry, Ying. Right. Okay. So yeah, go ahead.
Yeah.
Sorry.
Perhaps we could go to the next one.
Yeah. So with over the delay, we can go for the next presentation if you want to introduce the speakers.
Yeah. Excellent. Well, the third presentation, I'm really delighted that Mike is here as well. Juste, to make sure that I pronounce the name right. Juste, is it Raimbault?
Raimbault, yeah. It's also French.
Yeah, and of UCL, and has done a paper with Mike on building and validating modular urban transportation models using scientific workflow systems. And so Juste is again a PhD student, and
no,
really impressed. But
Juste is a research fellow.
He is a research fellow now, so
he's always been a research fellow.
He looks so young. So young.
Yeah, you look young. Actually, that's the problem.
Yeah.
That's the confusion. So well done.
And we look forward to hearing your presentation. The mic is here. Perhaps you should say a few words about yourself. Or Mike, are you going to say something yourself?
No, I'm not. This is Juste's presentation. Yeah. As he will explain, okay. It's part of the work that we've got from Daphne, the Data and Analytics Facility for National Infrastructure.
Fantastic. Yeah. Okay. Just say a little more about yourself, if you like. And
okay, so maybe I will begin by presenting myself. So I did my PhD in Paris, in Géographicité, on land use transport model on a coevolution of networks and territories. And then I did the first postdoc at the Complex System Institute, working on the validation of simulation models. And then I came to UCL, working with Mike on non-just transport models, and coupling models and so on. So this work is part of this. We actually had a small grant with the Daphne facility. I will discuss a bit more. And it's more methodological work, and it's also work in progress. So yeah. So I will go on with the presentation now. How much time I should aim for? Like 20 minutes? Or?
Yeah, do 20 minutes, and then we could do 10-12 minutes questions would be great. Yeah.
Okay, great. Okay, so the idea of this work is to provide some kind of framework using workflow systems, scientific workflow system, to build from the bottom up urban transportation models and to validate them in that context. So as I think everybody knows, and we saw a lot of talks since this morning using the MATIM model, for example. So when you begin to go to large-scale agent-based model and disaggregated models, it becomes huge, and you need a lot of heterogeneous data, and you need to integrate many different submodels or submodules. But so the infrastructure becomes big, and validation becomes complicated. So this example is from this paper where they couple the MATIM with first demand modeling. But then you also need to include data processing to have the correct files, and you need also to couple this with model post-processing analysis to get some statistics and so on. So you see it's a huge coupling of different models. And it's just for the MATIM model, which is a transportation model. If we go more generally to land use transport models, it's even more complicated, and there is this very good review by Michel at the time, which reviewed at the time. So I think it will be even bigger now. But a large set of LUTI, land use transport interaction models, and classifying them as progressively complexifying. So you can either complexify the transport model or complexify the land use model, but you see that in the end, you end up with a very complicated model, which can be multimodal, activity-based for transport, and also activity-based for land use model. And you see that all the different existing models, so most of these are kind of operational model. I think a lot of these models were discussed in this conference before, like the Schwanus or the Ercud and so on. So all these models include very different processes and very different submodels. So an issue with this is the idea that these are difficult to validate and to apply, especially in the long term to planning. So it's also a well-known debate in the community. And there was this paper back in 73, the Requiem for large-scale models, saying that these models are always intrinsically flawed, and they cannot reach their goals, and that they're not useful in terms of planning. And actually, Mike wrote a comment on this not long ago, saying that the new current of smart cities, urbanetics, and so on may follow the same path, like ignoring the complexity of cities and ignoring. So there is a kind of forgetting the past and just thinking you're able to predict everything in cities. when it's the contrary, that cities are always more complex through the technology we put in them. So what we propose to foster the relevance of still using this kind of large-scale models, we propose that we need transparency both on data and the implementation and reproducibility of these models. And the idea of validating both the integrated models and also the submodels. So going from small simple models, but that can be quite well validated to larger integrated models. So yeah, it's really the idea that if you got open and reproducible models, then you can share them and you can couple them. You can test them and validate them into modular integrated models. So why using a workflow system for this scientific workflow system? So just to give a bit of background, in all generative workflow system, scientific workflow system, is aimed at executing some numerical experiment and also data processing. So most of them today are for data processing tasks, like notebooks are kind of a workflow system. In a systematic, reproducible, and also it's kind of domain specific. So each scientific domain has its own workflow systems, but it's always systematic and reproducible. Often they are coupled to high performance computing infrastructure. So you can execute your numerical experiment workflow on HPC infrastructures. And the idea you have a high flexibility with scripting language to describe your workflow. And it fosters also easier scientific collaboration and reproducibility. So just repeating a bit myself, but the proposed approach is to build a modular transportation model from the bottom up, using this kind of workflow system. So there are several points, so it's also repeating a bit. But you can easily replace submodels that you put into the workflow. So imagining you got your land use transport models, you can just replace the transport model with another one, but just still keeping the same architecture and the same workflow. Then yeah, it's more easy to reproduce and also to benchmark, because if everything is open and modular, you can easily compare either the integrated model or the submodels between themselves. Then it's also easier to transfer the application of models. So if you got some generic workflow, you will see in the case study that we apply the Batty model to many urban areas in the UK, and you can do that automatically through the workflow system. So you got quite easy transferability of model applications. And you can also, depending on the workflow system you use, some workflow system has some integrated validation methods. I will also come back on this, and you can apply them to validate your model. Okay, so this is a case study. I will give a bit of results later on. So the case study is to build a 4-step multimodal transportation model using only open source projects and open source data. Mostly open source data, at least free. So what model do we include in this? So the well-known Batty model for the transport model in itself. Then, as you may be aware, when you need to generate upstream MATSIM, all the daily plans for individuals. So you need to generate transport demand. And for this, you need first a synthetic population. And for this, we use the Spencer model developed by the team of Nicola at University of Leeds. So it's also an open source project to generate synthetic population for the UK. Then to generate the homework flows for travel demands and generate plans, daily plans from this, we need a spatial interaction model. For this, we use a quant model, which is developed mainly by Mike and Richard Milton at CASA. And finally, there are a lot of data processing tasks and spatial algorithm. For example, to construct the spatial network from GIS data. And for this, we use a spatial data scalar library which is developed by the OpenMol community, and mostly myself actually. Okay, just a bit more detail. I won't go into too much detail on the parameters of the model and so on, because it will take too much time, but to give a bit of idea on the implementation and the data. So the data is, the implementation is quite generic for any functional urban area in the UK. So we use the functional urban areas provided by GHSL, so it's kind of normalized worldwide. It's better. And then we use the NOMIS data, so the census data for the Spencer model, and also the ordnance survey road. So everything is open data, and you can run it on any functional urban areas in the UK. The workflow system we use, I will come back also on this later. It first the Daphne facility, so it's a facility funded by UCRIC, and also the OpenMol software, which is an open source workflow engine. So what is currently implemented is the coupling of the Spencer with a model to have uniform job location for the plans, and then simple homework commuting. The network and plans are prepared into my team file and then fed into the MATI model, which is for now only one mode, so only car. And all the models are integrated, so both into Daphne and OpenMol as a Docker containers. So you Dockerize your model and then you can couple them. I will show this later. And this is still work in progress to integrate the quant model to have more realistic workflow. So I won't give any results on this today. So more detail on the Daphne facility. You can go on their website and you can actually ask. So registration is not open. You need to write to them, but it's open to any academic in the UK, I think. So you can ask for an access to the Daphne platform, and it's in a release process, and it's yeah, it's quite stable and quite performing. So it's a platform which developed initially for infrastructure research, so for the NISMOD models and so on. And there are a lot of pilots model. They actually also have a champion program, which is the funding we got. And so a lot of people are putting model on the platform. So the idea is you've got a different dimension. You've got the data sharing aspect. So people put their data on the platform and you can get the data sets. People also share the models. So you can upload your model as a Docker container and you can reuse the model that people upload. Then you also have high performance computing. So when you run your model, it's run on backend large scale servers. So they've got a huge cluster. I don't remember all the technical specification, but it's quite huge. And they've got this workflow system where you can integrate your models. So this is how it looks when you build your transportation model using the bricks and the workflow system. So you see that this is on Daphne. And Daphne workflow system is a visual workflow system. So you've got small boxes representing the model step that you couple together. So this is a simple workflow for a MATI model. First, you process your network, then you run your Spencer model for the population, then you run your MATI model, and then you visualize the results. You can also do a bit more complicated experiments and yeah, workflows inside the Daphne platform. For example, doing looking at the influence of stochasticity on model outputs, and so iterating on the model and repeating the model with the same parameters, but with different random seeds, and looking at how it changes the result. So it works like this. You get your iteration, and so in iteration set is the same as the model before. So network, population, matching, and then you visualize the results. It's a small example of what you can do, how you can visualize into the Daphne platform. I didn't mention it before, but there is this visualization part which is integrated into the platform, and it comes as Jupyter notebooks. So when your model is finished, you can get all the data files into some notebook integrated into the platform, and then write some scripts to do some plots and some maps and so on with the model results. Okay, so this is just an example of a map of MATIM trips. I think the urban area is Taunton. It's a small one because I ran the test on the small one. I don't know exactly where it is. I think it's in the west of UK. And so all the lines are the trips, and the color gives the time of the days when the trip is on. I also did the same with Leeds. And here we see with Leeds that we have there is an issue with sampling the population. So for tests to decrease computation time, you need to have a small part of the population, and here it's not so some populated area are less sampled, but others. So there are some issues with this. So the result are still test. But then, if you got your generic model as a workflow, you can apply it systematically on any urban area. So this is an example also of test results on all these areas. So basically, I took the largest one in the UK, but we are missing a few ones like London, because London was too big and it's still running actually. And a few other ones failed for some reason, but we have for now all these ones. And obtaining the result was quite fast, because Daphne allows you to run all this in parallel. So you can just run my model for all these areas, and you will run it in parallel and gain a lot of times. So what this plot shows is a distribution of trip distances. So trips obtained with the MATIM. So after the iteration of the MATIM model, you go to kind of equilibrium. So I had only 5 iterations. So it's not the equilibrium yet, but it's a stage where agents are already adapted their plans, and so it's more optimal trip distance for the agents. And you can then study this the distribution of the trip distance, and see that depending on the areas, you got very different distribution of trip distance. So for some areas, like Portsmouth or Nottingham, you got longer trips. Some are very localized. I think Oxford is the most localized area, so it's smaller, and some are more sprawled. So you capture this kind of urban sprawl through the car trips of people. We can also have a look at daily travel patterns. So, for example, what are the departure time of trips during the day? So the x-axis is seconds within a day. So you see the 2 peaks of going to work and coming back. And one interesting thing is that for the evening, it's much more spread, and it's much more localized in the morning. And it's obtained through the adaptation of the agent. So I don't know exactly why, but people adapt themselves more in the evening. So there are more flexibility in the evening trip than the morning trip. And you see that also depending on the urban area, it can be more spread in time than over, so over and more localized for departure time of trips. Another experiment that you can easily do with the free system, and I showed actually the Daphne workflow to do this. So it's to do some Monte Carlo experiment on the same urban area. So here is still the Taunton, I don't know how to pronounce it, Taunton, this small urban functional urban area, and to run it a lot of times. So here we have 10 repetitions, and we see that due to the stochastic noise, we've got different distribution. Here it's also trip departure time. So it means that the model outputs are quite sensitive to noise. what should be done next is to compare this level of noise to this the differences between urban areas, and see if the differences between urban areas are significant or not, depending on the noise. So all these are examples of numerical experiments you can do with your workflow systems. Okay, then it's something which is currently under progress. So I will give the methodology and the context. Is to do, for example, spatial sensitivity analysis on these models, and look if the spatial structure of your data and possibly the spatial structure of your missing data has an influence on model output. So it's a workflow it's a method we developed with Clémentine Cotillon, which is a former CASA researcher, also Romain, so other contributor of the OpenMO platform. And the idea is to extend traditional sensitivity analysis to the spatial initial condition of models. And within that context, you may need to generate spatial synthetic data. So we also got other papers generating this kind of data. So this will be applied to the Matty model and to the couple model. Then I will finish my talk by mentioning the OpenMO workflow engine. So OpenMO is actually a model exploration software, which is open source, developed since 2010, roughly at the Complex System Institute in Paris, mainly by Romain. And the idea is you have a free access. The first is model embedding. Second is access to HPC resource. So it provides transparent and easy access to any HPC resource, like a cluster, like a computation grid, or like a server. And then it also provides some extraction and optimization and validation algorithm. So you can go on the website and download it. So this workflow system does not work with visual workflow, but works with a script. So there is a domain-specific language built on Scala, where you specify your workflow through the script. So this is an example. You've got your graphic interface, and you've got your script within the workflow system, and you specify. So I will detail everything. So this is an example of the coupling the spacer with a quant model in an OpenMO workflow. So you specify, for example, in the middle, you specify the quant model, which is a container task. So it's still a Docker container. And you specify input and output of the model. And then in the end, you just specify coupling with the spacer, with the processing of operation, with the quant model, with post-processing. So you specify your model like this. And you can also write with Scala code some data processing tasks, for example, are directly embedding into the script. So why use the OpenMO in that particular context? So the idea is really to use the methods that OpenMO provides. And OpenMO provides a lot of advanced validation methods. So all these kind of methods, sensitivity analysis, so like global sensitivity analysis and indices and so on. Also spatial sensitivity analysis, which I mentioned before, are integrated into the platform. A lot of design experiment, calibration algorithm using a genetic algorithm to calibrate your model. Also diversity search to look at the patterns that, so the diversity of patterns a model can produce. Also algorithm for inverse problems and also model reduction algorithm. And here it's an illustration of integrated OpenMO into Daphne. So coupling in a sense the two workflow system to have the methods and then apply the methods to the modular model. So apply this validation method to the modular model I developed. So I will conclude with a bit of discussion and mention most of the development that are currently ongoing and that are the next step in this project. So integrated quant to generate commuting pattern, constructing a multimodal MatSim, so multimodal data for MatSim. And also, it's another part of the work, not directly linked to MatSim, but maybe in the end, have a dynamical strong coupling of quant and Spencer. What are the applications of this? The idea is validating this model we use. So, for example, validating one part of the MatSim model or validating one part of the Spencer model, and then it will enable validation of the coupling of the two. And using this kind of advanced model validation method. Then also one final objective of the project is to use the MATIM output to quantify the densities in public transport and then produce some exposure indicators in the COVID context. So it was actually the initial idea which motivated this coupling. And then in the end, test some policies and intervention on the transport system dynamics. So just to conclude, the idea is really to provide a methodological framework and context for open, reproducible, and validated urban models, which becomes the elementary bricks toward larger integrated models. So all the workflow I presented here are available. Actually, not the Daphne workflow because they are not available as script, but the OpenMol workflows and also the Docker container and so on are available in this GitHub repository. And also the spatial data library is available in the GitHub repository. And you can go check the website of the workflow engines. So thank you very much.
Thank you, Juste. Any question on this presentation? I need to open the chat and look at the audience as well in case the hands are up. Okay, Jamil, go ahead. Jamil, your hand is up. Is that that you have a question to raise, or is it from the previous time?
Oh, it must have been up from before, actually.
All right. Not worried.
Could I ask one question while others think of questions? At the moment, I think it's probably a related trend. So I applaud this work because of looking at modular models is a great thing. I cannot remember what it's now called, but in computer science now, people are developing tools which avoids extensive coding, sometimes avoids all coding. So basically, you could take these as building blocks and then you build models. Is that right? What is it called? So you are the expert. So you could actually tell us.
I'm not aware of. Are you mentioning like a functional programming where you can reuse some bricks and in the end you?
That's right. So these are developed so that for example, layman could simply just take the whole block into a live flowchart, and then this will put your data through, basically.
Okay, I'm not really aware of this kind of initiative. So I guess it's in a data processing context, or this kind of thing. It's basically the same idea that you've got your generic task, and you don't need to go into the details of it. So it's really this idea of modularity, and you can also benchmark these. So benchmark these bricks. Against everything. Yeah, I guess it's a general trend in many.
So I mean, I think it's important. It's helpful if you, and I am trying to elaborate on what Ying said, and then please correct me. If you can give us some sort of like an overview of the stages, the blocks of the code in your work. So understanding is that you, instead of like going into intensive transfer modeling side, you're trying to work it out bottom up. So getting the information from the transfer models and fuse it with the land use model, which you get from elsewhere, and then try to bring them together. And I assume that there is a data pipeline as well for regular arrival of the data, and sort of like the presentation studio, like a data studio type presentation at the end. Is it a bit of like elaboration of how the pipeline and the wrap up in this dynamic system works?
So the idea is to couple your blocks, you've got actually this kind of data pipeline, and you plug outputs of one brick as input of one other brick. So I don't know if we will see it here in the
somehow, but I think
it's a bit complicated here. Or maybe I can show the Daphne platform. But okay, the idea here in the OpenROS script is you've got input file and output file, and it's everything go through files between the containers. So at some time you need to. It's true that it's not as modular as I'm saying it is, and as easy I'm saying it is, because you need to have some kind of adapters between the bricks and some. And in the end, you can couple what is lookalike. Like you need some kind of correspondence between the two models. And for now, everything I mentioned is at the same scale, for example. But I know that Ying worked with Roberto Murcio at Casa, trying to couple the Luisa model with, I think it was with Quant. And the thing is, it was at different scales, and they had issue with this. I don't know all the details, but the issue that it was not exactly the same data, it was not exactly the same processes, and so on. And then you begin to have issues coupling. And it's actually when your model don't have the same ontologies, you end up with a problem. So yeah, what I'm presenting is a model that you can that are close to each other in terms of scales and in terms of what you've got inside. And if they are not, you need an intermediate model that you need to build yourself. And it's actually what I did for the Matim example here, because as the output of the Spencer model, you don't have. I think it's described here. Spencer don't give you any plan and so on. So here there is an ad hoc model to generate this commuting plan for people. So it's an additional brick that you plug in here. But the one thing which is good with this approach is this brick can be reused, and and they can be replaced with something more elaborated. So when the quant model will mature and so on. So I don't know if I answered your question.
Yeah, that was really helpful. Thank you. And for the audience, there are actually some stuff in the chat actually referring to some interesting location where you can find more information on the block-based coding and low-code, no-code.
Oh, okay.
Type of thing, in case you're interested to get more about the concepts behind these thinkings. And also the Daphne website and or the OpenMOL software is advertised, as well as you can see I think all these codes, and correct me if I'm wrong, but you can find all these codes in the GitHub, which can be available for the people to actually to download or clone.
Yeah. Actually, the Daphne workflow are not available because they are graphical workflows and they're not specified. So it's so to reproduce it, you need to have access to the Daphne pattern. Then you will have access to it. But for the open workflow, yeah, they're available as you can do them on them. But and all the container file and so on are available. So you can generate the containers and so on by cloning the GitHub repo.
Brilliant. Tim, you have a question, your hand's up.
Yeah, just a simple clarification one. On my understanding of Spencer is that it integrates kind of future plans and people's movements in terms of reaction to long-term trends. But from at the moment, your integration of Spencer is kind of static or dynamic?
I use a static part of Spencer, so to generate the synthetic population. Because sorry, I didn't precise this, but the Spencer has different parts, and one part is a dynamical projection in the future. so dynamical microsimulation. What I use is just the part to train the synthetic population.
Okay, and so then as a linked question to that, how many of the model integrations that you have allow for a full dynamic feedback, or are these kind of a case of reaching an equilibrium and then passing across the equilibrium?
It's actually I did not think it through for the maximum coupling, but for the quant spacer coupling, so the last script I showed, the aim was to have this strong coupling in time, so dynamical coupling in time. So here you got your quant outputs that feed into Spencer, which then feed into quant and then feed into Spencer, and then run this in time. So, and you can do this in the workflow system by specifying a loop. It's not done yet, but we aim to do this. And I'm not sure for the maxim because these are quite different time scales, so I'm not sure we'll try to do it or not. But in principle, it should be feasible. Yeah.
I mean, I don't know if you're aware, there was some work to try and link MatSim as the transport layer in UrbanSim. I think there's a book that on digital, I can't remember what it was, digital twins for sustainable cities, I think, but they tried to link MatSim as the transport layer for UrbanSim in Belgium, for Brussels, I think. But this was a completely static connection, so it'd be really interesting to see if this kind of next generation allows for these strong links in time across transport and land use. It would be a step forward, I think.
Yeah, and I think actually that the results will be quite different.
Yeah. I mean, that was one of the things they find is that if you allow just these full static solutions and pass over just your equilibrium states, the word I'm looking for, then you don't allow for these kind of dynamic feedbacks, and you get very different results. Yeah. They're really interesting.
Yeah, very interesting, specifically as we are moving toward the era of like a population clock, fusing data which are varying over time with the more static behaviorally deep data which are coming from the traditional survey to predict the flows close to real time. And perhaps those can provide interesting APIs to feed into these type of analysis to elaborate further. So it's really interesting looking ahead. I said that we have the last 10 minutes, I think even less than that. Is it some sort of like a discussion you want to have, or like a summary? Specifically that I know that we caught initial interesting discussion for the first paper as well, and promised that it would be met at the end. So this is back to you.
Thank you. I just wondered, perhaps Mike has joined us midway through, and Mike may have already heard perhaps the second and third presentation, right? Mike, would you like to say anything at this stage?
Well, I came in the second presentation, right? Which towards the middle of it, and that looked a very competent piece of work. I mean, I was very interested in but I can't really comment on. I mean, I'm not a remote sensor or anything like that, so I can't really comment on the detail of that. I might say a couple of words about what Juste has just presented.
Yeah, that would be helpful
to give some.
That will reinforce this. Yeah, go ahead.
Yeah. To give some context, you can see Juste on the screen, and behind him he's got the logo Daphne, which means Data and Analytics Facility for National Infrastructure. Now, there are in the UK a number of models which have been built over a period of about 10 years, dealing with national infrastructure, water, electricity, transportation, and indeed Spencer, the microsimulation model, is part of that suite of models developed largely by civil engineers, led by a guy called Jim Hall, who's professor of climate science or climate at Oxford. Jim is a hydrologist, I think, originally. Anyway, these models have been built as a system of systems models, and they really are part of something called UCRIC, which is the UK research consortium in cities and infrastructure. UCRIC has a number of urban laboratories dealing with real-time thing, but it also has this facility called Daphne, which is really designed. Daphne is located at Harwell, the nuclear lab, and is quite well resourced, has very high performance computing, many GPU servers and so on. And this particular facility, or rather the Daphne project basically, is to make these models from the National Infrastructure Commission available to the wider, first of all, in the first instance, the wider academic constituency, and then potentially down the line, well, we don't know. But in other words, they're putting together a framework, which Juste, in fact, has talked about, which is a series of workflows which enable you to port your model there and to get advice to put it into a form where it can be linked to other models, basically, in that sense. So the essence of the thing is not necessarily to build better models. There may be parts of it which will improve the models in a way, but to actually stitch models together so that a user wanting to look at, for example, the demand for water in different regions of the UK would also be linked to population analysis, which the Spencer model would mirror in that sense. So, in other words, the models would interface with one another from the point of view of making them available to the potential users. That may or may not lead to better models. One doesn't know, really, in a sense. But the kind of thing that Juste has explained, really, is one aspect of this. There are several different models being developed in this particular wider context. For example, at University of Southampton, John Preston and Simon Blaney are developing the national transport model. These are all part of this big suite. And if you want to know the acronym of the name of the project which has developed the national infrastructure models, it's ITRC, the integrated integrated consortium on, I don't know. ITRC Mistral is the series of projects that have been developed over about 10 years, which really form the guts of Daphne in that sense. Mm-hmm. Mm-hmm. So that's the kind of broader context. The workflow stuff is to link, and our project is to link Spencer to Quant, and also Matsim to Spencer to Quant, as a demonstrator, really, to demonstrate this. And hopefully in time, you know, to look at problems which do need that kind of integration.
Yeah. Great. Thank you so much, Mike. That actually explains the context of this work, and it really looks like it breaks into a really new area of modeling. And I just wondered also that on the earlier session, Athanasios was trying to persuade us to abandon our desktops and laptops and go for sort of bigger commuting, just like the weather forecasters. So Harwell certainly will have facilities like that as well.
Well, I think one of the problems was that when this Daphne project began, we thought in CASA that our quant model could be ported to Daphne. In other words, we could somehow make it available. Our quant model is pretty integrated in the sense that the visualization is really part and parcel of the whole model. It's a set of web-based services, really. And in other words, if you have a model like Quant, it's exceptionally difficult to put it into the Daphne context. You can't really package it in this sense. Yeah. And so part of the effort is to see what sort of models and bits of models might be packaged. So your Louisa model, Ying, and is, as you know, I mean, you've been involved in this, that potentially could fit on Daphne, potentially, but it may need a lot of tweaks basically to be able to do that. So in other words, some of these models which are put into these different workflows do need to be tweaked pretty heavily before you can actually do it. It so happens that the ITRC Mistral national infrastructure models were all sort of fairly uniform in some sense, dealing with water, electricity, telecommunications across the nation. And so the coupling them together, there's not as very strong predictive capabilities in those models. They're highly descriptive in some sense. And so consequently, they don't pose the same challenges as in, for example, land use transport models in some senses. And the other feature I think that Juste has talked about is the fact that some of these models that he's been putting together, like Spencer and Matson's, both depend on synthetic population databases, which are configured differently. So in other words, how do you kind of put those together, you know, in a sense, in this workflow thing? So that's really the nature of the project, to explore those sorts of things.
Yeah, well, it's a great path breaker like that, so it's great. Thanks, Mike. And I think we just reached the top of the hour. In fact, we're slightly past it. So perhaps colleagues could